As promised on the previous page, here's a little bit of notation and a new vocabulary word. This expression here that we worked with on the previous, built and worked with on the previous page, is called a derivative. That is just the slope of a curve. And the notation here is read as f prime of x. Okay, so it's just a little tick mark, and we read that as f prime. And this is called the derivative. It can be viewed, since we're building a function, it'll be viewed as a slope function for the graph of f. And it'll be at any value in the domain. So let's go through one that's a little more complicated than example 1 on the previous page. Same problem, we're going to find the equation of a tangent line. To find the equation of a line, we know we need a point. So we have our function, we have an x coordinate. If you plug -1 into g, you get -7. So we've got our point. I went ahead and found that already. And then our slope will come from the derivative. Always start out this way. That way you're not trying to plug things in from memory, you're looking at the formula. So g prime of x is the limit as h approaches 0 of g of x plus h minus g of x over h. And then we just have to plug things in. And this is where students tend to find difficulty, is g of x plus h. So if you just kind of go off to the side here, just a little scratch work, think about composition of functions. That's all this is. And think about what g does. I think it's better to think of a function without a variable. G does this to stuff. So whatever I put in here, this is what happens. So if I put an x here, I put an x there and there. If I were to put, say, -1, like I did above, we'd put -1 there and there. If I put a happy face, then I should do the same over here. Although they should be the same happy faces. Don't write that down, ever. It looks ridiculous. So the idea here is, if I put an x plus h here, then I should do the same here and here. Because what we do on one side of an equation, we do to the other. So that's the step where students tend to struggle a little bit. So if you have to, go off on the side and do what I did right here, and you'll find function composition a whole lot easier. So g of x plus h is going to be 3 times x plus h minus 4 times x plus h squared. So we have that minus g of x, which is just the original function. And be real careful that you use parentheses. Note how I'm writing things here. I'm putting both functions on top in parentheses and making a typo. That should have been a 4. So g of x plus h minus g of x all over h. That's the setup. If you can get to here, then the rest will just be algebra. So we know we're never going to be able to evaluate this limit as h goes to 0 on the first step, because there's an h down there. So with a problem like this, it seems reasonable just multiply everything out. Okay, so if I distribute here, I'm going to have 3x plus 3h minus, I'll get an x squared here, times a -4, so minus 4x squared. I get 2xh times a -4 will be -8xh. I get an h squared times -4, so -4h squared. This is a key place where I see mistakes. You'll know if you made a mistake if an h does not pop out on top. And often it's from not distributing this negative sign here to the second term. So we have minus 3x plus 4x squared. The reason that was important is everything without an h needs to go away. in order for me to factor an h out on top. And so if you look here, we have a 3x minus 3x, negative 4x squared plus 4x squared, and everything that's left on top has my h. So this will be the limit as h approaches 0. Let's just clean it up on top. We have 3h minus 8xh minus 4h squared over h. If I factor out an h, that'll leave me with 3 minus 8x minus 4h over h. Let me scroll down a little bit here. I remembered this time. So the h's drop. Let me rewrite this again. That gives me the limit as h approaches 0 of 3 minus 8x minus 4h. Now I can take the limit because we don't have a division by 0 issue anymore. And in taking the limit, as h approaches 0, 3 and negative 8x are constant with respect to h, so they go nowhere. And this expression right here goes to 0. So basically, at the end of these problems, the calculus part is just covering up all the terms with h's. Now, keep writing the limit until you actually take it. Okay. Otherwise, you'll have h's in your answers and you won't know what to do. So this ends up being 3 minus 8x. So g prime of x is 3 minus 8x. This is the slope of g of x at any x. So this is a slope function for our original function. Now we wanted, get rid of this stuff, we wanted the slope at -1. And we use the derivative notation, the prime notation, the same way as any other function notation. So I would find g prime of -1, which would be 3 minus 8 times -1, or 11. So this is my slope for this problem. So using point slope form, because I have a point and I have a slope, we'd have y minus a -7 equal to my slope 11 times x minus a -1. Be careful with all those negative signs. This is y plus 7. This is 11x. That's +1 plus 11. And so we get y is 11x plus 4. Just like the previous problem, I would graph both this and the original function in the same viewing window and kind of zoom in on x, or on the point -1, -7. Okay. So I mentioned we're not entirely interested in the actual equation. We're mostly interested in this number, the actual slope. But for now, for an intro problem, it's good to graph them both so you can actually verify what we actually found. Okay, so let's look at another, just to make sure you understand graphically what we're doing. Going back to the first example, we found that f prime of x, the derivative of f, was 2x. This is the slope of this function at any value of x that's in the domain. Okay, so we want the slope at these values. So when x is -2, f prime of -2 is 2 times negative 2, or negative 4. So that is the slope of the tangent line where x is negative 2. So that's at this point here. And that tangent has slope negative 4. So I just wanted to do this problem to make sure you have an idea of what we're actually finding. Because eventually, graphs are only going to take us so far. We don't know what most functions look like. So that's the slope at this point. We want to do the same for 0. So when x is 0, f prime of 0 would be 2 times 0, or 0. And that seems reasonable. If you look at the origin, any tangent line you draw would be horizontal. So certainly would have slope equal to 0. And then lastly here, we want to look at x equals 3, which is way up there. Almost off. So there's that tangent line there. And f prime of 3 would be 2 times 3, which is certainly steeper, so we get 6. So the slope of the curve there is 6. So notice that by building this formula for the derivative for the slope of x squared, we quickly get the slope at every single value. And the derivative is measuring slope the way it should. Where a function's decreasing, we get negative slope. Where the function's level, we get a slope of 0. And where the function is increasing, we get a slope that's positive. So slope is behaving the way it did for linear functions. Okay, let's look at some more examples on the next page.